Welcome to Study Loop.
Hello everyone, we are doing the problem 3.4 of Griffiths. So here we have to prove that the sum of two Hermitian operators is also an Hermitian operator. So for a Hermitian operator, we have F scalar product with H cap G is equals to H cap F scalar product with G. This is the definition of a Hermitian operator H cap for any two functions f and g in Hilbert space. Now we have to prove that the sum of two Hermitian operators is also Hermitian. So H cap plus k cap, where k cap is also an Hermitian operator, scalar product with g. Now we can expand this sum like f of H cap g plus f of q cap g. This is possible as this scalar product is just an integral. So integral of a sum is actually the sum of integrals. So here now, since H cap is a Hermitian operator, we can write this as H cap F scalar product with G. Also here also Q cap, sorry, this is K cap here. K cap F G. Now again, once again, we'll apply the sum rule and we have H cap plus K cap acting on F scalar product with G. So we see that the sum actually satisfies the condition of being a Hermitian operator, and hence the sum of two Hermitian operators is also Hermitian. Now for the second part, we have to prove that the product alpha q cap is also an Hermitian operator. So f of alpha q cap g, this is also an Hermitian operator alpha q cap for a Hermitian operator q cap. Now since alpha is this side, we can take out alpha like this. It's a constant f of q cap g. Now if we will write, if alpha q cap is Hermitian, then it should be equal to alpha q cap f scalar product with g. Now since alpha is on this side, the left side, it will come out but with a star, that is, it is the conjugate of the original alpha. Q cap f inner product with g. Now in order these two expressions to be equal, we need alpha to be equals to alpha star. So this means the condition that the two things to be Hermitian, we need alpha to be equals to be alpha star, which means that alpha should be real. So this is the condition required in order for the product alpha q star q cap to be a Hermitian operator. Now in the third part, we have to prove, we have to find out the condition for which the product of two Hermitian operators is Hermitian. So the product of two Hermitian operators f h cap k cap g is equals to, now since h cap is Hermitian, it will go on this side, h cap f inner product with k cap g. Now since k cap is also Hermitian, So it will go on this side and we will have k cap h cap f inner product with G. So we see that in order this to be Hermitian, we need it like this: h cap k cap f inner product with G. So we need h cap k cap to be equal to k cap h cap, or h cap k cap minus k cap h cap should be equals to 0, or the anti-commutator of h and k should be equals to 0. So this is the condition which is required for the product of two Hermitian operators to be Hermitian. That is, the anti-commutator of the two Hermitian operators should be equals to 0. Now in the fourth part, we have to prove that the position operator and the Hamiltonian operator are Hermitian. For the position operator, we have f inner product with x cap g is equals to, now we will use the definition of the inner product, integral f star xg to dx equals to x f whole star g dx. This is true because x is real, x is just position, and that's why it is equals to xf inner product with g. That means x is a Hermitian operator. Now for the next part, that is the Hamiltonian operator. The Hamiltonian operator is given by the inner product of the Hamiltonian operator is given by h cap g is equals to integral, we are just writing it out, minus h cross squared by 2m d2 by dx squared plus v applied on g dx is equals to integral f star d2g minus h cross squared by 2m d2g by dx squared plus f star vg dx. Now we need to prove that it applies equally on f star as well. So what we will do, we'll use integration by parts twice on the first part of this expression. So what we will do, we'll write down like f star integral, this is actually minus infinity to plus infinity, f star d2g by dx squared. Now we will use integration by parts to write it down as f star dg by dx infinity to minus infinity minus integral minus infinity to infinity df star by dx dg by dx. So one of the derivatives here has gone to this side because of integration by parts dx. Now again we will apply the integration by parts rule on the second term here, and after that we'll get f star dg by dx from infinity to minus infinity minus, now this derivative here will go to that side and we will have df star by dx g from infinity to minus infinity plus finally integral minus infinity to infinity d2 f by dx squared star g dx. So now since at infinity and minus infinity f star and g should go to 0 because in the Hilbert space the boundary terms vanish. So the only term which we will be left with is this term, which is d2 f star dx squared g dx. So we'll have integral minus infinity to infinity f star d2 g by dx squared dx is equals to integral minus infinity to infinity d2 f star by dx squared g dx, and hence we'll have, if v is assumed to be, the potential v is assumed to be real, we have f of h cap g is actually equals to minus infinity to infinity minus h cross, we are just substituting back in the original expression, d2 f by dx squared plus vf the whole star, we are just putting the star out whole here, this star is here now, g dx. So we have assumed here that v is real, so we have assumed that f star vg is vf the whole star g. If v is real, then we have this equals to h cap of f inner product g. So this proves that the Hamiltonian operator is also Hermitian. Thank you.